Hello. So good morning to you all. So welcome to the session. So how do we do some elementary vector analysis or elementary vector data analysis using GeoPandas? So just a quick recap of what we did yesterday. So yesterday I introduced you to a library called Pandas. So Pandas is a library in Python for reading and manipulating, or you can say in the term processing, the data which is in tabular structure. Like we saw the example of like maybe a spreadsheet, or suppose if you are reading data from a SQL table. So there were two primary data structures in Pandas. One is geo data frame, that is the entire table or entire spreadsheet, you can say that. And the second data structure was geo series. Geo series was like when you are referring to a single column from that entire table is called a geo series. Then we talked about the geospatial counterpart of Pandas that extends the, because Pandas cannot handle spatial data. So for handling spatial operations or spatial geometries, we introduced a library called GeoPandas. So there were two data structures in GeoPandas, like a geo data frame and geo series. So every geo data frame will have a geo series. So but a geo data frame can have more than one geo series, but out of those geo series only one will be its geometry. So then we saw that how do we read and write geospatial data using Pandas. So once after the data is written, now let us see that how do we create maps with GeoPandas. Like suppose if we have vector data available in any using shape file format or any different, like whatever we discussed, like there are multiple vector data formats, maybe GeoJSON or shape file. So now we'll see that suppose if we have data available in some of the vector data format, now let us see how do we visualize the data, or how do we create maps from that vector data. So right here I have a vector file called this is containing the tehsil or taluka boundaries of Uttarakhand. So I have a file with the name this tehsil.shp, which defines the outer boundaries of different tehsils of Uttarakhand. So for mapping, actually for creating the plots, GeoPandas at the backend uses Matplotlib only. So GeoPandas provides a high level interface to the Matplotlib library for making maps. So actually you need not call specifically Pandas. So Matplotlib. GeoPandas itself provides a high level interface directly for creating the plots. So directly on the geo data frame itself, like we saw yesterday, directly on the, you can call these plot functions directly on the geo data frame as well. So mapping shapes is as easy as just you need to call that geo series or data directly. So suppose if you are calling the plot function directly on the geo data frame, then the default geometry will be plotted. Otherwise, like if you have multiple geo series on your data frame, then you can call that on individual geo series also, you can call the plot function. So mapping shape is as easy as like just call the plot function on a geo series or geo data frame. Right, now let us see that how do we do this. So first thing, I am now the same file, I'm like for reading a shape file, we need to call the function dot read file that we discussed yesterday. So to the read file we need to pass an argument, the name of the file which you want to read, because here I have stored the name of file which I want to read in a variable called vector_file. Now I call the I read the file using the function gpd.read_file and vector file, and that I am assigning to the variable Uttarakhand. Now suppose if I want to inspect this geo data frame, then I can call the function dot head. So if I call this function head, then I can see that there are two attributes or two non-spatial attributes attached to this data frame. One is the name of the tehsil and another is the to which district this particular tehsil belongs, and there is a geometry column which defines the geometry of that or boundaries of that particular tehsil. So now suppose if I want to visualize how does this data look like, or I want to plot this on this, so then I can directly call the function plot. So directly geo data frame dot plot, if I call, the plot gets displayed on my screen. So now suppose instead of this I want to change the colors colors of this plot. Like instead of blue, suppose if I want to this fill color to be green, then I can pass it the color green. Then I can change the colors of edges also. Suppose if I want to change the colors of edges, then I can say edge color red. So this way I can change the colors of red, and suppose this face color I can say maybe none. So this way now suppose if I don't want the so just if I wanted to color just only the edges, so then I can pass the face color equal to none, and edge color I can say red, or otherwise I can pass any other color to the face also, like I want suppose blue. So this way you can change the appearance of your plot. So just on your geo data frame or geo series, if you call the function plot and pass it like different arguments, there are multiple more arguments that also you can explore and see it. So these are the basic arguments which are passing, like edge color, face color, and other things. So similar way, now suppose this was drawn on some color. Now suppose if you want to create some kind of map, maybe choropleth map or something from this using GeoPandas, let us see how do we do that. Now suppose if I have some population data also attached to this series, so I am just attaching a new column to this geo data frame. So here I am just creating some fictitious or random population and assigning that population to these tehsils one by one. So I am creating a data pandas series by calling just np.random.randint and numbers in from the range this to this. So, and because I am generating the numbers which is equal to the length of Uttarakhand, so whatever number of rows are available in this Uttarakhand variable, same number of values I am creating in this series as well. So now if I see pandas is not imported, so I will be just importing the pandas. NumPy is also not there. So if I see population, it will be look like this. So you can see that some random numbers got generated by calling this np.randint function, and now we will assign this column a name called population and append it to the our Uttarakhand data frame. So that how we will do. So Uttarakhand, and in square brackets the name of the column, and assigning it a new series, not geo series, it's a series. So now if I call Uttarakhand.head, now if you see that a new column with name population got appended to this Uttarakhand geo data frame. Now suppose if I want to make a, so there all the tehsils were colored using the same color, were filled using the same color. Now suppose if I want to make a choropleth map, so suppose I want to color the tehsils depending on the population of that tehsil. So I want to fill the color of the boundaries of, or I want to fill the color of area. Suppose if I wanted to fill the I want to give the color to each tehsil depending on their population. So suppose I want to create a map like this, or what you call choropleth map. Let us see how do this. So GeoPandas makes it also too easy to create a choropleth maps, like maps where the color of each shape is based on the value of an associated variable. So what is choropleth map? A map where the color of each shape is based on the value of an associated variable. So suppose here we want to make the color of every tehsil based on the value of the population in that particular tehsil. Okay, that is also quite as simple as calling the plot function. So here's the same thing, like I will call Uttarakhand dot plot, and here I need to pass another argument like column is equal to, based on which column you want to color the map. So here suppose if I want to color the map based on the column population, then I just need to pass the variable column equal to population. If I do this, then you can see now that the color of all these tehsils is a different color. So all these tehsils are shown in the different color, right? So now instead of using a single color for all these tehsils, a different color is being used for the tehsils. Now anyway, you don't know that from this, just by this color, because there is no legend attached to this map. So from this color we don't know what is the population of this tehsil or that. So for that we need to attach a legend to our map which describes like this color corresponds to this population, this color corresponds to this population, right? So so how do we create a legend? So when plotting a map, we can enable the legend using the legend keyword argument. So now if I pass another argument to the plot function like Uttarakhand dot plot, that column, and if I pass legend equal to true, then a new legend will be created and attached to the map. So right here you can see that a legend got attached to the map, like okay, this yellow color represents the population above 80,000. So this way then these dark colors are in population around 20,000 or less. So this way we can attach a legend also. Similar thing, now suppose if you wanted to if you want to change the orientation of this legend, so instead of it to be, you want it to be horizontally placed, then you can pass on some more arguments to the plot function like legend keywords. So there you can pass these arguments. The legend keywords will be a dictionary. So there you need to pass like label. So what label you want to attach to the legend, and the orientation. So orientation by default it will be vertical orientation, and suppose if you want to change it to horizontal, you can do it like this way: legend keywords, label, and orientation. Then figure size anyway is the size of entire figure. So this way you can create the legend to be horizontal or vertical, and then you can attach a label as well to your legend. So next things like here, then similar way, suppose if you want to change the color map, suppose if you don't like this particular color map, you can change the color maps as well. Then you need to pass another argument to the plot function like cmap. So in whatever color map you want, like accent, if I want the accent color map, then I can say this like, then if you want like jet, I may use the jet color map. This way you can choose different color maps. So the next thing is, now suppose if you want the flexibility in choosing these color map as well. Like now we have selected the default color maps. Now suppose if you want to change the colors scales of this color map, like the way maps are. So for changing the scales of this color map also, there are different functions available for classifying these data, so that those classes can be scaled to different values. So the way color maps are scaled can also be manipulated. So suppose if you want to change the way these color maps are scaled, so that also can be changed by passing a new argument called scheme. So there are GeoPandas support multiple schemes for classifying the data. So these there is a scheme option, and you can set to any scheme provided by the map classifier. Actually there is a GeoPandas on the back end uses the map classify library. So you can use, so map classify supports multiple ways to classify or rescale the data for the color map, like box plot, equal interval, Fisher-Jank samples. So these are the classification methods for scaling the color map are available to users. So you can choose any of these classification methods depending on how your data is. So depending on how your data is, you can select any of these classification schemes for rescaling your color maps. Like suppose if I wanted it to be the natural breaks, so then I need to pass the scheme is equal to natural breaks. Or suppose if I want it to based it on percentiles, then I can make it percentiles. Or suppose if I want to make the classes in equal intervals, so that in every class, let's see first the natural breaks. So this is most optimized classification scheme for quantifying the data. And then legend also we can pass. So instead of 10 by 10, I can make it 5 by 5. And then legend is already true. So this way you can create the map like this. Now suppose this is, you don't like this, then you suppose if you want to make equal interval class, like, so that in every class there are so there is an equal interval. Actually the color is scaled equally, or otherwise suppose if you want in every class to be the same number of samples, then you can call like percentile. So percentiles or natural break, whatever way we want to, like head, tail breaks, Janks, caps also. So there are so many functions. So this way you can change the color scales of your color map. So once this is done, created. Now let us see how do we create multi-layer maps. So till now we have just plotted a single feature or attribute, such a single feature on a map, and we have given. We saw that how do we change the color of that map. Now let us see how do we create a multi-layer map. Now suppose you have data like you have a layer where there are only points, and we have another layer on that where you have polygons. So now suppose if you want to visualize those layers, those two layers together, one on the top of another. So let us see how do we create multi-layer maps. So one more thing is that we need to ensure before plotting any multi-layer data is that the CRS or coordinate reference system of both of these layers must be the same. So they must be aligned. So they must be the same. Otherwise, the data will not align properly. So before combining the maps, we must ensure that they share a common CRS. Otherwise, your map will be wrong. Right. So let us see how do we create a multi-layer maps using GeoPandas. So here same thing, I am just reading the Uttarakhand vector file. So if I see Uttarakhand dot head, so this is the detail of my Uttarakhand variable. Now suppose now let us see what in which CRS the data is there. So if I call Uttarakhand dot CRS, so it says that it is in EPSG 4326, and so Uttarakhand is in EPSG 4326 or geographic coordinate system. So now suppose for this Uttarakhand itself, now I'll creating a new. So I am just copying this Uttarakhand geodata frame to a new variable called Tehsil headquarters of Uttarakhand. Like suppose if I know that because if you know that for every Tehsil there will be a headquarters. So suppose we assume that the city headquarters or Tehsil headquarters, suppose we want to represent them as a point. So now we want to plot the points on a polygon, on the top of a polygon in a single map. So I have just copied it. Now suppose I just want to change the CRS of this. So how do we change the CRS of this to some EPSG 3395, so that I just want to, I am reprojecting it to a projected coordinate system EPSG 3395. So how do we reproject image or reproject vector data using how do we so this is the way to reproject a data frame, right, by calling the to_CRS function. So if you call to_CRS function on a geodata frame, so the geodata frame gets reprojected to the new CRS. So here I am. So then you can pass on this like EPSG code or WKT string also you can pass. So here we are directly passing the EPSG code of the new projection system. So Tehsil headquarters to CRS EPSG 3395. So we are reprojecting this to 3395. Right now, so here we are assuming that, suppose if you assume here that the headquarter of every Tehsil, so every Tehsil is a polygon, is the we are assuming that the headquarter of every Tehsil is located as the centroid of that polygon. So let us, so let's see how do we calculate the centroid of each of these polygons. So there are multiple polygons in Tehsil HQS. Suppose if I see now the CRS of this. You see that it is now in projected coordinate system and EPSG 3395. Now I want to calculate, like I am assuming here the fictitious headquarter of every tehsil to be located at the centroid of that geometry. So I am creating a new column in my tehsil headquarters. So that will be a type of geometry, that will be a geometry only. So here what I am doing, tehsil headquarters dot geometry dot centroid. So for every feature in the tehsil headquarters file, I am calculating the centroid of that polygon and assigning it to a new column in the tehsil headquarters data frame with name HQ. Now if you see tehsil underscore HQS, now it has two geometry columns. You can see that one is the geometry with the name geometry and another is with HQ. A new column got added here, HQ, and so this has points. So in this every feature is a point feature, right? So we have created the centroid of, so this HQ is a centroid of each of these polygons. So this way, just by writing a simple command, we can calculate the centroid of our geometry, and we have attached this to our data frame. So now here you can see that now our data frame contains two geometries or two geoseries. You can say not geometries, contains two geoseries. So out of this, one can be the geometry only, but only one of this can be the geometry. So suppose if I want to see that which is the geometry column of this, dot geometry dot name, if I say, sorry. So it says that presently the assigned geometry of this geodata frame is the column geometry. Now suppose from this tehsil headquarters, now I want to change the, now if I plot this tehsil headquarters, so it will see that its default geometry will be plotted. Dot plot. If I see now the polygons only are plotted. Now suppose if I want to change the geometry of this geodata frame. So now I want to make the HQ column as the geometry of this geodata frame. So for that, like as we discussed yesterday, so the function available for changing the geometry of a geodata frame is the function dot set underscore geometry. So set underscore geometry, and this which column you want to make the new geometry of our geodata frame. So tehsil underscore HQS. Now because this other column with the name geometry is not required, so I am just dropping that from the geodata frame. So tehsil headquarters is equal to tehsil headquarters dot drop columns is equal to geometry. So with this, the column with the name geometry is being dropped from the geodata frame. Now if I plot the tehsil headquarters geodata frame, you can see that only points are shown because we had calculated the centroid of all of these pixels and assigned them to a new geoseries called HQ, and now this HQ geoseries is the geometry of our column or geodata frame. So when we are plotting the tehsil underscore HQS, it is just showing the points. So now this these points are available are in the projection system or CRS of this tehsil headquarters is EPSG 3395. Actually we converted it to EPSG 3395 just for calculating the centroids of these pixels, because if centroid we are calculating in EPSG 4326 or geographic coordinate system, actually the calculation becomes incorrect. So just for calculating the correct centroid, we reprojected it to the projected coordinate system. So now our tehsil headquarters are in EPSG 3395 or this is UTM projection, world Mercator projection. So now suppose if you want to create a multi-layer plot of, in the first layer we will be showing the boundaries of tehsil, and in the second layer we want to show the headquarters of each of these tehsils together. Now because these are in two different projection systems, so first we need to bring them to a same or common projection system. So first thing, what we are doing, we are reprojecting the Uttarakhand geodata frame also to the EPSG 3395. So how do we do that? By just calling the function to_CRS. So if I call this, and then if I see the CRS of Uttarakhand, so this is also now in EPSG 3395. So now if I see the plot of Uttarakhand, now you can see that this is showing now in meters. So if you see the previous plot, it was in latitude and longitude. So 77.5 to 81 and 29 to 31.5. Now this got, because we have converted it into meters of projected coordinate system, now the values you can see I have changed. Now let us see how do we create the multi-layer plot using these two. So this on the base layer will be this polygon boundaries, and on the top of this we will plot the points. So for that we will be using the second approach what we discussed about in Pandas. So instead of directly calling the plot functions, so we will explicitly create first figure and axis, and on those axes we will plot our data. So how do we create a figure and axis? So in matplotlib, so first thing we need to call the subplots function. So in matplotlib.pyplot we have a function called subplots. So subplots creates a figure and an axis on that figure. So first thing we have created this. Then first thing we are calling Uttarakhand.plot. So on Uttarakhand.plot, but we are not just blindly calling Uttarakhand.plot, and we are passing it few more arguments. Like first argument we are passing axis. So on which axis this data to be plotted, because here we have created an explicit axis. So we are passing this axis only to be the axis of this plot. So AX equal to X, AX whatever we have created here, and then color, like the fill color of these bound polygons, and then edge color we wanted it to be in black. Now suppose if I just call this plot will look like, okay, PLT is not imported, so I will just, so I have missed calling the matplotlib.import. I'll be calling it here. So if you see, the plot looks like this. So here we have defined that color to be white or none we have passed, so it is showing as white color, and the edge color we have defined to be black. So now on the top of this plot, now we want to plot the point layer. So point layers are available in the geodata frame called tehsil_HQS. So tehsil_HQS.plot. To this plot also we are passing the arguments like axis, on which axis or in which subplot of the main plot this data must be plotted, that is also on the same AX axis. Then we are creating, like for every point, because this is the point data, so what is the marker. So marker we are passing it as O, and the color red, and the size of marker. So here now you can see that we have created a multi-layer plot. So on the baseline there are the boundaries of our polygons, and on the top of that we have these points. So this way, by changing the color of this, you can change their color or size. So 10, or the marker you can change to maybe X. So this way then you can change the appearance of your plot, or like maybe star also, maybe marker. So this way then later on by annotation you can give them name as well, like this is the name of this tehsil headquarters and so on. So this way we can create a multi-layer plot using matplotlib. So once this is done, we are just deleting this. So next, let us see how do we manage projections. Anyway, this we have already seen how do we reproject, but let us just for the sake of completion, we'll see now how do we manage the projections of a geodata frame in more detail. So as you know, CRS are important because the geometric shape in a geoseries or geodata frame object are simply a collections of coordinates in an ordinary space. Now suppose if I show you just these numbers, so what is happening, because these numbers are just because these geometric shapes in a geoseries or geodata frame, they are just collection of coordinates. So first you need to know the reference of these coordinates, right? Then only it becomes meaningful. Otherwise I say 30, 40. So it doesn't make a sense until and unless we have a specified reference. So a CRS tells Python how these coordinates are related to places on the earth. So what is the coordinate system of these points? So how to interpret these numbers with reference to which point? So that is the job of CRS. So CRS tells the Python how these coordinates are related to the places on the earth, because 30 may be 30 in meters or maybe 30 degree. So with the help of CRS only, Python can determine, okay, how these places are related to the places on the earth. So for GeoPandas accepts a lot of representations of CRS, like in case of GDAL also was accepting the representations of CRS in multiple formats. So similar, almost may not be all the formats of CRS, but GeoPandas supports these. So you can specify your CRS in PROJ4 string. So this is the general format for when you want to specify your CRS in PROJ4 format. This is like plus projection is equal to long lat. So this is like a geographic coordinate system. Then ellipsoid WGS 84, datum also WGS 84 plus no underscore depths, or you can define it like a dictionary as well, like projection lat long ellipsoid WGS 84 datum, or directly you can specify WGS code also when specifying the CRS of your data, right? So let us see how do we set the projection of our geodata frame. Suppose now we are going to read the data from a CSV file, and there are just point locations only. Now we want to set the projection system for that geodata frame. So how do we set? So the projection system can be set by calling in your geoseries.crs. So geoseries.crs is an attribute there, it's not a function because we are not having parentheses here. So geoseries.crs equal to, then you can pass on a dictionary where you can say init, key is init and colon, then in what is the EPSG code of your projection system. So then you can pass like EPSG 4326. So once the projection system is required, now suppose if you have data from different sources, then you want to reproject them to a common projection system on CRS. So for reprojecting, as we have seen in the previous examples also, the function to be used is to_CRS. With to_CRS you can reproject your geodata frame. Okay, now let us see how do we do this. So anyway, now same thing, I am just reading the Uttarakhand file. So this is like presently the CRS of this is EPSG 4326 geographic coordinate system, GeoGCS. And suppose if I want to reproject it to a projected coordinate system, suppose if I want to project it to projected coordinate system, or where the units will be in meters. So the same function as we have used previously, to_CRS and the EPSG code of the destination projection system or destination CRS. So if I see now, let us do this. So our original Uttarakhand was available in GeoGCS, and we have Uttarakhand reprojected, a new data frame we have created, that is in Mercator projection. Let us see what is the difference between these two. So here you can see that, so this was, if you see the units here are in degrees, so 77.5 to 81, and the same when it is reprojected to projected coordinate system. Now these are in meters. So 8.65 into 10 raised to the power 6 meters to 9 into 10 raised to the power 6 meters. So this way, just by calling 2_CRS, we can reproject our already projected data. And suppose if you don't have any projection system associated in your file, then by calling .CRS, you can assign a project or CRS to your data or vector data. So now let us discuss about how do we do some basic geospatial analysis, or suppose if you have vector data and you want to do some basic geospatial analysis on your vector data. So we will discuss about geometric objects and what are the general attributes and methods available to these geometric objects. So like there are multiple geometric objects like these point, polygons, line, multi-line or polyline. So now with every of these geometric objects, there are multiple attributes and methods also associated with these geometric objects, so that you can do some manipulation on these geometric objects. So all geometric objects, may be line, point or polygon or multi-point, multi-line, they have at least these basic attributes and methods. Like one is object.area, like maybe a polygon.area. So this area calculates the area of that polygon. Then similarly these functions are like bounds. So this returns a min, max, like what are the bounds or extents of this particular geometric object. So it returns a float value that bounds the object. So similarly, like these are the length. So length will be applicable only for just for maybe line. So length, then geometric type, like what type of geometry it is, maybe like point, line or polygon. Then you can calculate the distance. Suppose if you want to calculate the distance of one geometric object from the another geometric object, so you can call object.distance. And then you can, suppose if you want to create a representative point, so representative point is a computed point that is guaranteed to be within the geometric object. So suppose you have a polygon, so you want to create a representative point for that polygon, so that the point will definitely be inside that polygon. So you can create a point by calling representative point. So these all methods and attributes are available to all of the geometry objects. So let us see now how do we create different geometric objects in GeoPandas. Actually GeoPandas is dependent on another library called Shapely. So Shapely is basically used for creating and manipulating geometries. So for suppose if you want to create a point object, so how do we in the Shapely? So from Shapely.geometry module, in the Shapely.geometry module, all these geometric objects are available. So you can import first from Shapely.geometry, import point. Now suppose if I want to create a point, so I need to call the point class like point, and I need to pass it the arguments x and y, longitude and latitude. So this will create a point with 10 and 0s. Now if you see here, if I have created just a point with 10 and 0, now I don't know whether this point is 10 degree and 0 degree or 10 meter or 0 meter. So for Python to interpret it properly or associate it to its location on the earth, so we need to define a CRS also, so that this 10 will be interpreted depending on the CRS, whether this is 10 degree or 10 meter. So then only it can be projected on the map. So for this, because of this only CRS is required. So here now we don't know what is the CRS attached to it. So how to interpret Python or even nobody doesn't know until we specify its units, that how to interpret this with reference to where this 10 is, how far from where it is 10 degree, from where this 10 is located. So whether it is located from center of the earth or first of all we don't know whether it is in degree or meters itself. So because of these reasons only CRS is important. So I have created a point. Now suppose if you want to call these all functions what we discussed on this geometric point object, so like geometry.type, if I call on this, it returns that this is a type of point. Now suppose if I want to calculate the area, because point will have no area, so if I call point.area, it says 0, and similarly if I call length also will be 0. Then points bounds will be showing the point around this, so all the 10 0 10 0. Then now if I just call point, it draws a point here. Similarly we can create line or line strings, like from shapely.geometry line string. Then here, instead of a single point, you need to define the pairs of these latitude and longitude, a combination of pairs of these points. So line will have more than one point, or these are the combination of these points. So this way we can specify the line string. So if I just call this, so these are the two end points. Here we have defined the two end points of this line, 0, 0 and 1, 1. So this has shown a line. So similarly, now if I call the area on a line, it will not be 0. Then I can calculate the length. So it says 1.41. So depending on these, we are assuming here this is in meters, 1.41 meters. Then lines, bounds. Suppose if you want to get the coordinates, like what are the end points of this line, then you can just call line.coordinates function and so on. So similarly, you can create a polygon. So polygon also is an ordered sequence of xy points tuples. The sequence may be explicitly closed. So suppose if you are calling a polygon function, and so what, because finally it should be a closed shape, right? So suppose if you are the sequence, so you may be explicitly close it, or by just using the same indices for the first, by using the same values for first and last indices. So you may explicitly close it. If you don't explicitly close it, your shape itself will implicitly close it. Like suppose if I specify a polygon, so how do we create implicit close? Suppose if I create a polygon by calling this polygon 0, 0, 1, 1 and 1, 0. So here the starting point and ending point are not the same. But as we are creating the polygon, so Shapely by default will make one more vertex, add one more vertex to this, where the end point also will be same as your starting point. So now if I call polygon, if I draw the polygon, so you can say that it has drawn a closed shape. So similarly, otherwise, if you explicitly also you can close. Here we have specified that our starting indices and last indices are referring to the same point, 0, 0. So this way you can make it explicit close as well. So now there's the same thing. Now in the polygon you can have these things like polygon dot length, area, or you can calculate the bounds. So it covers the 0, 0, 0 to 1, 1. Then you can do like geometric manipulation on this. Like suppose you want to create three different. Now let's discuss about the geometric manipulation. So how do we do some manipulation on these geometries? So here we have created three polygons, and then we can create polygons like buffers around this, and different like on these geometries we will apply some different geometric operation. Like here we have created three different polygons. Now if I see P1, now suppose if I want to draw a buffer of 0.10, 0.10, maybe we are assuming that these are in some projected coordinate system, and suppose if I want to create a buffer of 0.1 meters around this geometric shape, then I can just call the function like P1 dot buffer. Then it creates a buffer of 0.1 degree around this point. Then if I drop P2, P3, this is there. Now suppose if I want to combine, like these are three different observations. Suppose if I want to combine them to a geo series. So suppose I want to create a series by combining these three things together. So then I can call a function like like we are creating series using pandas. So here we are creating a geo series, and in the geo series we are passing these different features. So P1, P2 and P3. So a new geo series got created. Actually that is not imported. I'll be just importing this geo series. So I have created a series, geo series. Now if I see this GS, so here now is this GS, you can see this contains three polygons. Now suppose if I want to plot these all together, so I can, like in GeoPandas I was calling dot plot. So here I can see I plotted three. So these are in a single geoseries, so every feature got plotted here. Then in this geoseries you can calculate the area. So if you calculate the area, so the area of each feature will be calculated separately. So now you can see that it is showing 3 areas because there are 3 features in this geoseries. So the area of each feature got calculated individually. So similar way, suppose if you want to calculate a buffer around all of these features, and that will again be a geoseries, and if I see this, then you can see that a buffer around all of these features got created. Similar way, suppose now if you let us do some more geometric operation. So instead of creating our own geometries, some existing geometries, so here again I am reading the tehsil.gip, so tehsil boundaries of Uttarakhand, and I just plot this. This looks like this. So now suppose if you want to create a convex hull. So what is convex hull? Convex hull is the representation of the smallest convex polygon that contains all the points in the objects unless the number of objects is less than 3. So if the object if the number of points in the object are less than 3, it doesn't work properly. But if the number of points in that object if there are more than 3 points in that object, then if you call the convex hull on this geoseries, so it creates a smallest convex polygon actually, that contains all points inside that all points in the object. So convex hull is the polygon which contains all the points in our feature or geometric shape. So suppose if you want to create the convex hull around the Uttarakhand, like minimum convex polygon which covers all points of the Uttarakhand, then you can directly call this our geodata frame dot convex hull. So it will be creating the convex hull for all these feature geometries together. So if I do this and I'll call cs.plot, so it has created a convex hull or a minimum smallest convex polygon that covers all points of the all features in our Uttarakhand shapefile or Uttarakhand geodata frame. Then similarly, suppose if you want to create a envelope. So envelope is the representation of the point or smallest rectangular polygon. So this was a simple polygon that was covering minimum smallest convex polygon. So suppose if you want to create a smallest rectangular polygon, so that covers entire of your area, then you can call this dot envelope attribute. So call envelope, and if I call envelope around this, so this is the rectangular polygon covering all the points in our original feature. So similarly, suppose if you want to simplify or want to make a simplified representation of the geometric object, so all points in the simplified object will be within a tolerance. So with this we can create a simplified representation of the geometric object, and all the points in the simplified object will be within a because of the simplification they may shift here, but they will be within a specified tolerance to the original geometry. So suppose if you want to create a simplified representation of Uttarakhand, and you want that all the features should be within this tolerance 0.05 meters to the original geometry, then you can say that specify this parameter, and you want like to be topology to be preserved, so then you can pass it false or true depending on your requirement. If I see this you can see that this is the simplified representation of Uttarakhand. Then suppose if you want to create a unary union means you are just creating a union of all these features together. So this way you can, so it takes a bit of time, then you can create a unary union. So then similar way there are multiple other operations. So now if I see this UK, we'll see a simple geometry. because uk dot plot, if I go, so actually this is just a polygon, so it does not have the plot function, because for making it to plot we need to convert it to a geo series, then only we can make. So this way you can say it as create a unary union of all, so a union of all the geometries in this geo series. So now similar way, suppose if you want to create suppose Uttarakhand, I am just reprojecting it to a Mercator projection by calling this. And suppose if I want to create a buffer around the center of all these geometries, so that suppose if I want to create a multi-layered plot using this. So here what I am calling, I am creating a Uttarakhand dot centroid buffer. So like suppose so suppose if you want to create the buffer of some 5,000 meter around every of the, so the similar way like we calculated the Tehsil headquarters. Now here again on the Tehsil headquarters, now suppose if you want to create a buffer around all of these headquarters, so same thing can be done here, like dot centroid dot buffer. Now suppose if I plot this way, I can create buffer around these points. So there initially we just plotted these points. Now suppose if you want to create buffer around all these points, so that also can be done just by using these few more steps. So so this way you can extract some part of like to extract, so this way you can extract some like 1 degree to h square, you can just use intersection, and there are other operation like that we will discuss here, some geometric operations on these objects like intersection, union, and so now let us see how do we create a geo data frame from a CSV file. Now suppose if you have the data about, suppose now you have different monitoring stations across Uttarakhand. Now assume that we have some different weather monitoring stations around Uttarakhand, and we have in a CSV file their name of these stations and their location. Now suppose if you want to convert for visualizing these locations on the map, suppose if you want to convert this data to a geo data frame or a shape file. So let us see how do we do this. So here I have a file name called stations.csv, which contains the location of these stations. Like suppose now first I will read the file using pandas. So df equal to pd.read underscore csv with this file name, and if I inspect this file, so you can see that in this file these are the columns like station ID, name, station, and name of or code for that station, and latitude and longitude, their position. Now suppose for I want to visualize these locations on the map. So for that I need to convert this data to the vector data, right? So that I can, so for that I need to convert these, combine these latitudes and longitudes together and create a point geometry from these latitudes and longitudes. So how do we do that? So for this I am in pandas there is a function called gpd or geopandas dot point from xy. If you call this function point geopandas dot point from xy and pass it like for which all like your two series is like gpd dot points from xy, and then I am passing it x and y. So df dot, or I can say df longitude, or I can say like this also df latitude. So here what we are doing, so gpd dot points from xy and passing is this column df latitude and df longitude. So all the rows in these two columns will be converted to point geometry, and finally we are combining them all these points in a geo series, right? So if I see this, so as obvious, I think the previous function it is working. Now it is giving that some error warning, it is giving safely deprecation warning. So this function will be, as for this function will be deprecated in the future. So we need to convert them to vectorized dot point revive. So you need to call this function, or we need to pass coordinates in a numpy array. So these are not numpy, this is a pandas geoseries. So in future we need to convert them into numpy arrays. So anyway, right now it is working. So if I print this, so what it says, it has created a point geometry by combining this latitude and longitude, like you say 30.7 and 77.86, 77.86, 30.70. This way it has created a point geometry by combining the latitude and longitude column. Now this I can create a, because now previously we have a pandas data frame. Now this pandas data frame we can convert to a geo data frame. So for creating a geo data frame, the function like gpt.geo data frame. So in this we are passing the arguments like convert which one first, or original data frame, and the name of the geometry column. So from this data frame, which column to be interpreted as geometry column to this. So geometry we are passing that this geoseries geom call. So now if you see this, a new geo data frame is created, and in this these are the non-special attributes, and a new column geometry got added to this. Now this geom call is the geometry in our column. Now if I plot this GDF, now you can see that these all got plotted as points. So this way we can convert, if we have our data in a CSV file, we can convert to them to a shape file or a vector data format for visualization on the map. Then actually now if you see this, in this we had not set the CRS. So if you open it using some GIS software, so that will complain that projection or CRS is missing in this. So now first we need to attach a CRS also to this geodata frame. So for that, the same function like whatever we were calling set underscore CRS. So geodata frame dot set underscore CRS, then we need to pass it EPSG code or whatever it is, because these are in latitude and longitudes. So we are setting it at to be EPSG 4326 or geographic coordinate system. So if I set this, so once this is done, now suppose if I want to save, because geodata frame saving is as same as like calling the to underscore file function, and I will give it the file like csv underscore file dot shp something. So what says column name larger than 10 characters will be truncated when saved to ASRI save file. So I think in this some columns are there with the whose length is more than 10 characters. Names of the columns are more than 10 characters, because ESRI shape file name of the attributes can be maximum for 10 characters. So it has just truncated those names, that warning it has given. Now here a csv underscore fill must have been created. So I'll see name csv underscore fill. So now here you can see that this SHP, these all shape file plus its auxiliary files have been created. So this way we can convert our CSV file to the shape file. Now let us discuss briefly about the different set operations with overlay. So in the geometries you can apply different set operations like union, intersection, difference or symmetric difference. For this there is a package called there is a function called overlay function. So creating new shapes based on the places where data sets overlap or don't overlap are often referred using the language of sets. So suppose when we want to create new shapes based on where data sets overlap or don't overlap are generally referred in using the language of sets. Like in the sets we say union, intersection, difference or symmetric difference. So these operations are available in GeoPandas through the overlay function. So like here you can say that this is the intersection. Intersection means the area which is common to both of these geometries will be called intersection. Similarly union is the combined area of all these two. So wherever these two are there, so this is the combined area of all these two geometries. So symmetric difference is so excluding the common area. So all the area excluding the common area is the symmetric difference. So the difference is the area which is coming in A but not coming in B. So area exclusively only in A is the difference. So these are like set operations only. So let us see how do we apply these overlay operations in this. So for this we are creating two polygons, and these are the locations of these polygons, and let us visualize these P1 and P2. So these P1 and P2 we are P1 we are creating a geodata from P1, and we are creating another geodata frame from this polygon P2, and then we will apply these set operations in these plots and visualize the data. Now suppose if I am going to plot this GDF1, so these polygon, this looks like this, and GDF2 is like this. So these are also this. Now we will make a combined plot of these both together. Now let us see. So here we are plotting these GDF1 and GDF2 both together. So in the GDF1, so GDF1 color is red, and in the GDF2 the color is green. So all red color is GDF1, and so this is first geometry, and this green color is in second geometry. Now we will use an overlay function and calculate like the intersection of these two geometries, difference or union of these geometries together with overlay operation. The overlay function will determine the set of all individual geometries from the from overlaying the two input geodata frames. So overlay function works directly on the geodata frame. So now let us see, suppose how do we create a union overlay. So suppose if you want to create a union of these two geodata frames, so how do we do that? So this is simple, directly from the GeoPandas there is a function, as we said, gpd.overlay, and here we are passing the two geodata frames and how we want to make the union of this. So gdf.overlay GDF1 and GDF2, and how a union. So now if I see the resulting union, so this is a geometry. Now if I plot these together, so here AX, what I am creating, union.plot. So in union.plot is my union area. So like you can see that this face color is none. So because these internal ones we have not shown their face color, and this red and black are our original things. Now if I see just before this, so you can see that this is the union of all this, because their color map you have used tab 10. So this way, because now this is the union of all these, so all geometries combined together. So this is the union, and on this, suppose if you want to demarcate our GDF1 and GDF2, so here on the same plot we are plotting this GDF1 and GDF2 with the edge color red. So wherever you see the red, so red means our GDF1 and black is GDF2, and this is our combined or resultant union of the GDF1 and 2 combined geometry. So this is our combined geometry, and these are like we have combined this the red edges and black edges together in a single geometry. So now this is our resulting geometry. So similarly, suppose if you want to calculate intersection, so then just you can call dot overlay and how intersection. Now if I plot them both together, so you can see that this colored portion is the intersection of these two geometries, like these reds are GDF1 and blacks are GDF2, and this colored are the intersection of these two geometries. Similarly, you can calculate symmetric difference. So this is the symmetric difference. So the area except the common area. So this black, green, this white area was the common, and these all red areas are the symmetric difference. So excluding the common area. So similarly, you can calculate the difference. So difference means the area like we have calculated GDF1 minus GDF2. So area which is on GDF1 but not in GDF2. So GDF1's area which is not in GDF2. So this area was common with GDF2 as well. So this area and this got excluded, this red got excluded, and this only has come. So this way you can apply any we can apply this set, union, intersection, or difference or symmetric difference operations on geodata frames using overlay operation. So this was like, there are some other things, because of the non-ability of time I am not able to cover this. Then you can, there are multiple other things, like you can combine multiple data frames by joining them together, or you can dissolve the different geometries together, and so on. So thank you very much for attending